Hey everyone, welcome. Today we are diving straight into a massive topic for your Cambridge IGCSE computer science exams, logical binary shifts. Whether you're studying syllabus 0478 or 2210, understanding exactly how a computer manipulates data at the bit level is absolutely fundamental. We're going to figure out how positive 8-bit binary integers are shifted, what happens to their decimal values, and how you can lock down those top marks on your exam.
Here's the roadmap for this explainer. We're kicking off with an introduction to binary shifts, then moving into left shifts for fast multiplication, right shifts for fast division, what happens with 8-bit limits and overflow, and wrapping up with how to ace those exam questions.
Part 1. Introduction to Binary Shifts, or as I like to call it, CPU math secrets.
Let's start with a really fundamental question about how computers actually think. You know, computers process everything in binary, right? Just zeros and ones. But how on earth do they multiply or divide so incredibly fast? They definitely don't memorize times tables like we did in primary school, and they aren't sitting there doing long multiplication. Instead, the CPU uses a brilliant hardware shortcut called a logical binary shift. This happens right inside the CPU's registers, which are those tiny, lightning-fast storage areas.
So what is a shift? Well, it literally means picking up all the bits inside an 8-bit register and moving them left or right by a set number of spaces. Think of it like a row of 8 chairs. Imagine everyone sitting in those chairs suddenly just shuffling one seat over to the left or one seat over to the right. That is exactly what a logical shift is doing.
All right, part 2, left shifts, which give us fast multiplication.
Let's see how this shuffling trick actually works as an instant multiplier. Picture an 8-bit register holding the binary number for 21. If you remember your place values from right to left, we've got a 1 in the 16 column, a 1 in the 4 column, and a 1 in the 1 column. Add those up, 16 plus 4 plus 1, and bam, 21 in denary.
Now, watch closely what happens when we do a one-place logical left shift. Every single 0 and 1 slides exactly one spot to the left. So that bit in the 16 column, it jumps to the 32 column. The bit in the 4 column moves to the 8. Now, an empty space opens up on the far right side. We always fill that empty gap with a 0. And here's the magic part. If we add up our new active columns, which are 32, 8, and 2, our denary value has perfectly doubled to 42.
This brilliantly shows us our very first golden rule. Every single shift to the left multiplies your original number by the next power of 2. So 1 shift left multiplies it by 2, 2 shifts left multiplies it by 4, 3 shifts multiplies by 8, and so on. It's literally how digital electronics do multiplication at breakneck speeds.
Moving on to Part 3, right shifts, which, as you might guess, means fast division.
Okay, so if left means multiply, then right means divide. It just makes perfect sense. Let's start with the decimary number 200 sitting in our 8-bit register. We've got a 1 in the 128 column, a 1 in the 64 column, and a 1 in the 8 column.
Now we're going to perform a logical shift one place to the right. All the bits slide to the right. That 1 from the 128 column shifts neatly into the 64 column. This time our empty gap opens up on the far left, so we drop a fresh 0 in there. Add up our new columns, 64 plus 32 plus 4, and look at that. Our value is perfectly halved down to 100.
Just like with multiplication, the rule here is super predictable. Shifting right divides your binary number by the next power of 2. 1 shift right divides by 2. 2 shifts divide by 4. 3 shifts divide by 8. This is a massive game changer for things like embedded systems or graphics processors that need to quickly scale values down.
Part 4, 8-bit limits and overflow, or what happens when math goes totally wrong.
So, what happens when we simply run out of room in our fixed 8-bit storage? Cambridge examiners absolutely love testing you on this. An 8-bit register is essentially a box that holds exactly 8 items. You literally cannot squeeze a 9th item in there. But before we break the register, you need to know 2 crucial definitions. The most significant bit, or MSB, is the bit all the way in the far left. It has the highest place value, like 128. The least significant bit, or LSB, is on the far right, with the lowest place value, which is 1.
Now, let's bring back our number 21 from earlier. If we take 21 and shift it left 4 times, we're telling the computer to multiply 21 by 16. In theory, that should give us 336. But wait, The absolute maximum value an 8-bit register can hold is 255. So as we shift left 4 times, that one bit that started in the 16 column gets shoved completely past the 128 column and just falls off the edge. It's completely lost. Our register now reads as denary 80, which is totally wrong. This is what we call an overflow error, and it means our data has basically lost its precision.
And yeah, things can go horribly wrong with right shifts too. Say we want to divide 189 by 32. That takes a 5-place right shift. But any bits that get pushed off the LSB side on the right, they are gone forever. Basic math tells us 189 divided by 32 is 5.9, but our shifted register gives us a denary answer of 5. Why? Well, binary registers don't do decimal points. Logical shifts just ruthlessly chop off the decimal fraction.
The syllabus actually spells this out, and it's a golden rule you need to memorize. Bits pushed off either edge are lost forever, which totally compromises the data. And at the exact same time, any empty spaces created at the opposite end are always filled with zeros.
Part 5. Acing the Cambridge exam. Let's talk top tips.
When this pops up on your exam, trust me, it will, here's how you secure full marks and avoid the traps that catch thousands of students out every single year. These are the most common mistakes. Students will shift right when they're supposed to multiply, or they'll leave empty gaps in the register totally blank instead of putting a 0 in, which will instantly cost you the mark. Or they try to write decimals like 5.9 in their denary answers instead of just whole integers. Do yourself a massive favor, pause this explainer right now, jot these down, and promise me you won't make these easily avoidable mistakes.
If you want to guarantee that A star, use this incredibly simple 3-step strategy to double-check your work in the exam hall. First, just perform the binary shift they ask for. Second, convert your brand new binary number back into denary. Third, ask yourself, does the math check out? Like, if you shifted 2 places left, is your new denary number exactly 4 times larger than the original? If it is, you've completely nailed it.
All right, it's your turn. Pause this explainer and try it yourself using the rules we just went over. Take the binary number 00110110. Now, perform a logical shift 1 place to the right. Work out the new binary and then figure out the new denary value. Go ahead, I'll wait.
Okay, how did you do? By shifting every single bit 1 place to the right, that rightmost 0 just falls off the edge. Then we plug a fresh 0 into the empty, most significant bit slot on the far left. That leaves us with 0001111. Convert that to denary, and you get 16 plus 8 plus 2 plus 1, which perfectly adds up to 27. Our starting value was 54, so our 1-place right shift accurately divided our number perfectly in half.
Awesome job! You have officially mastered logical shifts for positive integers. But before we go, I want to leave you with a bit of a brain teaser for next time. If a register uses 2's complement to store negative numbers, where that far left bit acts as the minus sign, what do you think happens if we logically shift it left and push that sign bit right off the edge? Chew on that for a bit. Make sure you review today's masterclass to really lock in the basics, and I'll see you in our next explainer where we dive into the wild world of negative numbers.